In this video, I'm just going to look at some more examples dealing with our trig identities and showing you different techniques that we might use to simplify these identities. The first example that we want to look at is if we have 1 over the cosine of x minus cosine x. So here, one of the techniques is we could think of this cosine x as being over 1, and we can simply get a common denominator. So this would remain 1 over the cosine of x. And if we multiply here by the cosine of x on the bottom, we would multiply the top. So therefore, we would get cosine squared x, because once again, we want to get a common denominator. So therefore, we have cosine x. So we would have 1 minus the cosine squared x over the common denominator cosine of x. All right, now we can see that we have 1 minus cosine squared on top, and this looks like one of our Pythagorean identities. And if we look closely, we will see that we have sine squared x plus cosine squared x is equal to 1. And if we were to subtract over the cosine squared, we would get sine squared x equals 1 minus cosine squared x. So therefore, all of that turns into sine squared x over the cosine of x. And it depends on if you're trying to simplify this to a certain answer. This could be simplified to lowest terms, or we could go a step further. At this point, we could split the sine squared into sine of x times sine of x, and then think of this as sine x over cosine of x. And if we do that, then sine over cosine will go to the tangent of x multiplied by the sine of x. So this is probably about as simplified as we can go at this point. Now, if you're trying to match this up, you may realize that this could be a possible answer if you're looking at multiple choice. Either one of these is probably simplified to your lowest terms. A lot of times, if possible, you're going to simplify your answer like we did here at the end, so we do not have a denominator. Okay, so one technique here that we just learned is if you have an expression, we can get a common denominator to combine your terms. All right, the second example we have is sine squared multiplied by secant squared minus sine squared. And this one here, we're going to notice that we actually have two terms, and they both contain sine squared x. So therefore, we're going to factor out sine squared, and if we do that, we'll be left with secant squared x minus 1. And once again, if the trig functions is making this hard to see, think of this in place of sine squared, we could call it x squared, and secant squared, we could call that y squared minus sine squared, so that would be x squared. So if you think of x squared, y squared minus x squared, we have an x squared in common, so if we factor that out, we get y squared minus 1. So this is just a technique you might want to use to help you factor the trig functions. Now at this point, we have sine squared x and secant squared x minus 1. That looks similar to a Pythagorean identity. So if you look at their identities, we see that if we have a secant squared, it's actually 1 plus tangent squared x, which is equal to secant squared x. So if we were to subtract the 1, we would have tangent squared x is equal to secant squared x minus 1. So then all of that is going to be equal to the tangent squared. And that would be our final answer. So once again here, another topic, technique rather, to look for is if we have a common factor to factor out that greatest common factor. All right, the third example we have is the cosecant of x minus sine x. Now here you notice we have a reciprocal function, the cosecant of x. Normally we think of that as 1 over sine x. And then if that's minus sine x, well, the only way we can really combine this is just like we did with an earlier example, is to come up with a common denominator. So the common denominator is going to be sine x. So this is going to remain the same. And over here, that means we need to multiply this denominator by the sine of x, which means then you're going to multiply the numerator by sine x. So the numerator will become sine squared x. So now that we have a common denominator, we can subtract 1 minus sine squared over sine of x. And once again, this top piece, 1 minus sine squared, looks like one of our Pythagorean identities. And that's our sine squared x plus cosine squared x equals 1. And we subtract away the sine squared, so that leaves us with cosine squared x equals 1 minus sine squared x. So the numerator will go to cosine squared x over the sine of x. And once again, we could possibly stop here, but if we want to get rid of the fraction, to get rid of the denominator here, once again, we could split the cosine into cosine x multiplied by cosine x. And then if we have this over sine of x, then we would have cosine over sine, which would be the cotangent of x multiplied by the remaining cosine of x. Okay, so now we look at our next example. We have 1 over secant x plus 1 minus 1 over secant x minus 1. And once again, we have two fractions. In this case, we're subtracting. So in order to combine these together, we need a common denominator. So that means we need to represent each of these factors. So that's going to be our common denominator, secant x plus 1 and secant x minus 1. So here we have the 1 on top for the first fraction, and we have the secant x plus 1, but we need to multiply by the secant x minus 1. And then for the other fraction, we already have the secant x minus 1, but we need the secant x plus 1. So that means we need to multiply the numerator by secant x plus 1. Now here we need to be careful. We have our common denominator, so we can write all of this over secant x plus 1 secant x minus 1. And then 1 times this is just going to, 1 times secant x minus 1 is simply secant x minus 1. Now over here we have to be careful because we're actually going to distribute this negative sign. So it's going to be a negative 1 times secant and then a negative 1 times 1. So therefore you're going to end up with a negative secant x, and a negative 1 and a positive 1 would give us a negative 1. So at the numerator, secant x and a negative secant x, they're going to cancel each other out. Negative 1 would be a negative 2. And then on the denominator, we can go ahead and multiply this out. Secant x is secant squared x. And when we multiply here, we get a negative secant x, and the middle piece is going to give us a positive secant x. So the middle terms are going to cancel out. So the only thing we have left is 1 times negative 1, which is negative 1. And again, this is where you should get in the habit. You start seeing a trig function squared with a 1. Does this look like one of our Pythagorean identities? And if we look closely, we have one that contains secant squared, and that is 1 plus tangent squared x equals secant squared x. So here, if we rewrite this, secant squared x minus 1, that means we have tangent squared x. We need to subtract 1, so that has given us x secant squared x minus 1. So all of that's going to be equal to the tangent. So therefore we have a negative 2 over tangent squared x. And there's really nothing wrong with this particular answer, but again, to make it look a little bit nicer, we can take and rewrite the tangent squared. If we keep this in mind, this is 1 over tangent squared. Well, what is 1 over tangent squared? Well, 1 over the tangent is equal to the cotangent. And because it's squared, it would be cotangent squared. So we could write negative 2 multiplied by cotangent squared x. So here with this example again is looking at how we can find a common denominator, and then after finding the common denominator, we can use trig identities to simplify the remaining fraction. And keep in mind, anytime you have, in this case, 1 over tangent squared, we could use the reciprocal identity, which is the cotangent, to eliminate the fraction. All right, the next example, and this one's going to be a little bit different. We have the cosine squared of pi over 2 minus x, and this is all divided by the cosine of x. Now, one thing I want to point out here is if we look closely, notice we have both cosine functions. The top one's squared, the bottom one's not. But the other thing is, if we look closely, on the bottom, we're taking the cosine of x. Okay, so we have an angle, this angle is x, and then the numerator, we have the cosine of pi over 2 minus x. So you'll notice when we use these identities, the angles have to be the same. So if possible, we would like to be able to rewrite this pi over 2 minus x as an x to match the cosine x on the bottom. And this is where if you see pi over 2 minus x, or this would be 90 degrees minus x, this is looking at our cofunction identities. And that's the one where we have the cosine of pi over 2 minus x is going to be equal to the sine of x, because remember we have sine and cosine, they sound alike, the cofunction, sine, cosine. So that's where we're saying the cosine of pi over 2 minus x will equal the sine of x. So that means we can take and rewrite the numerator, instead of writing this up here as cosine squared pi over 2 minus x, we can write it as, because it's squared, it would be sine squared of x. And now that matches with the cosine x on the bottom. And I think at this point you could simplify this to eliminate the denominator. We've done this a couple times now. We could think of this as sine x split out the sine squared, and then we can put the cosine on the bottom, and sine over cosine is going to be equal to the tangent multiplied by the remaining sine of x. Okay, so keep in mind the cofunction identity. If your angles don't match up, in this case, with where you see a pi over 2 minus x, that's a indication you're going to use a cofunction identity. Okay, one last example. We have 1 plus the tangent of x multiplied by 1 plus the tangent of a negative x. And once again, notice here we have different angles. One is x and the other one is negative x. So before we can really multiply this, we need to make sure we come up with the same angle. And this is where this doesn't match with the one we did above. This was your 90 degree or pi over 2, so this was the cofunction identity. This one is just simply looking at your angle being positive and negative. So this is sounding more like one of your odd function or even function identities. And in this case, the tangent function is an odd function identity. And if we recall, for your odd function, if we're looking at the tangent, what does that tell us? Well, that says that if we were to take the tangent of x, that would be equal, or let's write it this way, the tangent of a negative x is going to be equal to the opposite of the tangent of a positive x. So up here, we can rewrite this tangent of negative x using the odd function identity. So we would end up with 1 plus tangent x, and then this is going to be multiplied by 1. Now, instead of tangent negative x, that's going to make this go to a negative tangent x. So it's 1 minus the tangent of x. Now, what was the advantage here? Well, now we can look and see that here we have the tangent of x, and over here we have the tangent of x. So we have eliminated the negative x up here on the top. So now we can simply multiply this out, and to do that we can use the FOIL technique. So 1 times 1 is 1, and once again, if we multiply here, we get a negative tangent and a positive tangent, so that middle term, two terms are going to cancel out. So we're simply left with a tangent multiplied by negative tangent, which is a negative tangent squared x. And once again, you look at this and you think that looks like one of our Pythagorean identities. So if we go to one that contains tangent, we see that it's 1 plus tangent squared x equals secant squared x. And this is where you will notice that here we have a positive sign. It says 1 plus tangent, and this one over here is negative, and there's no way that we can get that to match up. So this here would simply be your simplest terms.